In this lecture, we are going to motivate the definition of a linear space or a vector space and then provide it. So, one of the most natural and long-standing examples of vector spaces was possibly from the notion of a force. Recall that a force in physics was denoted by the following, by an arrow like this. The direction of the arrow is the direction in which the force is acting. And well, obviously we think that it is acting on this particle A, on this particle here, and the length of this okay, this length is the length gives the magnitude of the force. So there are two things the moment we come into a force. One is its direction, and the other is the magnitude, the amount, how strong the force will be. Now, one important observation is in the resolution of forces. What does it mean? In the resolution of forces, it means that if we have a force acting in this direction, say, and another force, let me draw it with another color. So there are two forces, one acting along the black line and the other along the blue line. Then how would the particle move? Well, the suggestion is, if there was a single force acting on this particle, then the particle would have moved from here to this, in this direction. So what will be the direction in which the particle will move if these two forces were acting on it? It was observed that it could be seen if we could really complete this parallelogram with these endpoints. Okay, if we could complete this parallelogram, then it would be in this direction along the diagonal that the force would finally resolve to. So this is the resultant. This is often called the resultant force. So let's give some name. Let's call this force U and a force V. Okay, and it is often called the parallelogram law of these forces. So, and from geometry, well, this resultant is often said to be U plus V. Okay. And from geometry we know that before we go, let us say that if we call this force U, we often write over here for the magnitude like this. We say this is the magnitude of the force. And from geometry we know, how to calculate the magnitude of U plus V in terms of this, and the angle theta between the lines or between the directions of U. Okay, but that was one first observation, was about the resultant of forces. And given some finitely many forces, therefore, we could possibly find out the resultant using this formula. And the next were a few observations. Firstly, it doesn't matter which force U or V actually acted first on the particle. So, irrespective of which one acted first, the resultant is still the same. So, which in general demands that this must be equal which is often referred to as the commutativity. Of the resultant. Furthermore, if three forces acted, then obviously, say U, V, and W, we could first find the resultant of this V and W, and then look into this. Or we could find the resultant of U and V, and then find the resultant of W with this. But however, the idea is about three forces. So the line of action again line of final action will not depend in the particular order in which the resultants are commuted. So this must also be the same. So this is often called the associativity. Now, how do we denote a force of twice the magnitude of the given force u? Well, obviously, its line of direction will be same as u, but its length would be just be the twice of what we had. So the magnitude will differ. So the magnitude actually tells us about the strength of the force. So if we must have something like this, if lambda and mu are real numbers, a force which is lambda plus mu times the magnitude of u, well, it is nothing else but the resultant of these two forces. Because in this picture there is nothing, theta is 0, so it is just the addition of the magnitudes. And similarly, the scale, if you have this, a lambda times the resultant of u and v must be this also. Well, over here, where are just real numbers. Well, I have said real numbers, yes. What would be minus u? Minus u would be the same force as u, but in the opposite direction as u, but the magnitude being the same. So we therefore immediately come across the notion of the fact that when u and minus u act on the particle doesn't move. So there should be a force denoting denoting no action on the particle. And which we will write as 0. So what does it mean? For every force, the resultant of this and this of the 0 force must be same as u itself. And then I should have the inverse force, or okay. So okay. And one more thing about magnitudes which I should have said is, this is quite obvious about now it turns out that our parallelogram law, so these observations, these demands written under these stars are very natural expectations from the notion of a force acting on a particle and its resultant. And they happen to be true for this description of this forces, of this resultant of forces. In fact, these basic observations underlie a whole lot of examples. So these basic observations underlie several other phenomena and hence merits the criterion of being singled out and studied. And this is exactly the notion of a vector space, which we now defined. So a vector space V is a set such that along with two operations for each pair there exists a unique vector element of V denoted by U plus V and called the addition V. And for each U in V and lambda in R, there exists a unique element of V denoted by lambda V called scalar multiple okay. These two operations satisfy the following laws. Okay. So this is exactly a vector space. So it has two operations. One is called the addition, and the other is called the scalar multiplication. The addition is commutative, and associative. Then this is about the existence of identity for the addition. This is existence of inverse. This is about 5, 6 and 7 are some distributive properties, and finally the most natural thing is 1 times this must be this. 1 times a vector must be the vector itself. So that's it. We will first look into several examples of this in the next video lecture. In the last lecture, we saw the definition of a vector space. Let us review it once more. And here it is. It's a set along with 2 operations. For each pair of vectors, there exists a sum. For each vector in a scalar, there exists a scalar multiple. And the sum is commutative, associative. There is an identity for the sum, and everything has an inverse. Every member or every vector has an inverse, and the scalar multiplication satisfies the distributive law with respect to vector addition, with respect to scalar addition, multiplication, and the trivial condition must be stated. Before we go to any further examples, let us look into some consequences or some remarks. Which will make our lives a little bit simpler. The first one, so to each vector and to each scalar lambda, there exists a unique vector denoted as lambda times u. So therefore, I am saying that from this set whose elements are this, I produce a function okay. So this is a function okay, and this function is the scalar multiplication. Okay, and the properties of these functions are exactly 5, the last few actions, that is 1 times v is v, then lambda mu times v is lambda times mu times v, lambda times u plus v is, and lambda plus mu times v is okay. So these are the properties. Okay. Regarding the addition to each pair of vectors, so this is a set of pairs. We associate a unique vector called the sum. So this shows that it is a binary as a function, and hence a binary operation. On V. And what are its properties? The properties are, so let me put these properties as bullets: associativity, commutativity, existence of an identity and inverse. And the existence of inverse. Now a few more on the lines of the existence of identity. The first thing to observe the identity. Is unique. So let's give a quick proof. Suppose 0 and say 0 prime are two identities. So therefore it says for all u in V, u plus 0 is u, and this is same as u plus 0 prime. Okay. So therefore in particular from this side I get 0 prime plus 0 is 0 prime. Okay. So that is giving me this, and from this part I get 0 is equal to 0 plus 0 prime, but so what do I get? And the commutativity tells me that these two are same. So it says 0 prime must be 0. A quick proof. Okay. And so it's called the, hence the 0 vector. By the way, the members of let me put that over here. The members of elements of V are called vectors, and real numbers are often called scalars. Okay. All right. So hence the 0 vector. Then another thing needs to be looked, the inverse of each vector is also unique. awesome. And how do I prove this? Let's have a quick proof. Let for u in V and W be inverses. That is, u plus V is the zero vector, and this is same as u plus W. Okay. Now, let's see. Then V is obviously V plus 0, which is obviously same as 0 plus V. Now, why do I do this? I can make this in the first step. Is 0 plus V. Then this is U plus W plus V. But U plus W is also W plus U plus V, where I am using commutativity. By associativity, this is same as W plus U plus V, which is W plus 0, which is equal to W. Okay, and hence we shall denote this unique inverse of U by minus. Obviously, minus U is nothing else but minus 1 times U. Okay. So this is also something which we can quickly prove. And I leave it as an exercise. Okay. So these are some few things. So what do we need to look for a vector space? We need to give a binary operation on V. We need to give a scalar multiplication satisfying these properties. Having said so, now let's have a look into examples. Obviously R, if I say R is itself a vector space, why? The addition, so let me say the vector addition What is the vector addition? It is the usual addition of real numbers. And scalar multiplication is the usual multiplication of real numbers. Okay. R2. So it's a set of pairs. And what is the vector addition? It's component wise. And what is the scalar multiplication? One can carry on. So Rn is the set of all n tuples. Where n is greater than or equal to 1. And I am defining the vector addition again coordinate wise, and the scalar multiplication also coordinate wise. Okay. Well, these are all vector spaces. Verification has to be done by you. Okay. Let's look into something else. Recall let V be the set of all functions let me put a specific symbol. Let X be a set. Okay, and R the set of all functions okay. Now I am going to define the vector addition and scalar multiplication. Let f g be functions and lambda be a real number. So I am defining the vector addition. I have to define a function f plus g. So this is the function defined from x to r which takes okay, that is f. So the way I write this, it is just another way of saying that f plus g at x is fx plus gx. Okay, and what is the scalar multiplication? I have to define this function lambda times f from x to r. It is x going to lambda times fx. Show that this is also a vector space with all possible. This is also a vector space with the these two operations. So let's have our next example. Remember, the set of all functions, real valued functions we have just seen, is a vector space. Let me now take this to be C to be the set of all continuous functions. F on the 0-1 closed interval and taking values in R. And again, obviously, C is a subset of the set of all functions, real valued functions on 0-1, and we know that this is already a vector space. So what will be the vector addition in C? In C, we utilize the vector addition and scalar multiplication of this bigger one, of this bigger vector space. So f plus g is exactly the pointwise sum as we had earlier, and lambda times f at x is lambda times fx. Since the sum of continuous functions is again continuous, and scalar multiple of a continuous function is continuous. So we now know that plus defines a binary operation, and this is also a function from R cross C to C, the scalar multiple. So this is a vector space. We can make it even better. D be the set of all differentiable functions on so again we have and these two are already known to be vector spaces. Since the sum of differentiable functions, the scalar multiple of a differentiable function, are all differentiable, so D has the vector addition and scalar multiplication as in C. Okay, so it makes another vector space. Good. We have another. We take P this is the set of all polynomial functions and just to recall, a polynomial function is of degree n is given by specifying, so I should say, okay, specifying n plus 1 real numbers A0 An such that Px for x in R. The numbers are the called coefficients A0 is often called the constant coefficient, constant term, or the constant coefficient. An is said to be the leading term or the leading coefficient. And over here there is a restriction. An shouldn't be 0 and n is said to be the degree of the polynomial. And we often write n is said to be the degree of Px. Okay. So then we have the set of all polynomials, and again we take, so if and lambda is in a real number, then the sum of two polynomials is quite simple. Take it pointwise again, and the scalar multiplication is also simple. Take it pointwise again. So that makes this to be a vector space. There's another example. Here is another example. I take Pn to be the set of all polynomials, set of all polynomial functions whose degree is at most n. Okay, and take vector addition and scalar multiplication to be exactly as in P. Okay. So this again makes a vector space. Observe that P1 is a subset of P2, is a subset of P3, and so on. So this is an increasing ladder of vector spaces, and all of them is contained inside P. All right. So there are several such examples. We complete this with an esoteric example. Call to give a vector space, we need to provide a binary operation on V called its addition. It's the name. The addition is the name. Addition of vectors is the name of that binary operation. It may not actually be in any sense addition, neither they could be numbers or whatever. As we have seen already, then the elements of the vector space are not numbers. So we are defining a binary operation and we call it the addition. Okay, and these are subject to what are the rules? Commutativity, associativity, existence of an identity, and the existence of inverse. And the second one is we have to provide a scalar multiplication. That means a function from R cross V to V. And what are they subject to? Some distributive properties. And the triviality, the trivial equation. Okay? So these are the properties. Okay? So now, here my set. So now is the definition. My set V is the set of all positive real numbers. Now I need to define a binary operation. So I take a pair of real numbers, positive real numbers, and I take my binary operation to be the multiple or the multiplication of x and y. The usual multiplication of x and y. Obviously, since multiplication of positive reals is commutative, we know this from childhood. It's associative. 1, the number 1 is its identity. And for x greater than 0, 1 upon x is its inverse. Okay? So it's a plausible candidate for the binary operation. Next, I want to give you the scalar multiplication, which means a function from R cross V to V. That means I take a real number lambda and I take a positive real number now x and I take it to the lambdath power of x. Obviously, x to the power lambda is again another positive real number. And let me check. Checking of the properties. So first thing I have to check is remember this thing. This is the rule, okay? Now, what does the left side mean? This is lambda plus mu, scalar multiple of lambda plus mu with x. So it is x to the power by my definition, it is x to the power lambda plus mu. Now herein comes the laws of indices. So this is nothing else but x to the power lambda times x to the power mu. But x to the power lambda is nothing else. So this entry is interpreted in my example as this. X to the power lambda is nothing else but lambda times x. X to the power mu is mu times x. And this plus, which was the vector addition, is nothing else but this multiplication. So the laws of indices says that this rule holds good. Okay. Next comes the property I wanted to say okay. All right. So now let's make it a little more colorful then. Scalar multiple of lambda of x plus y. But x plus y is interpreted as xy. And this to the power scalar multiple is this. Okay. Now again, by my law of indices, this is x to the power lambda times y to the power lambda. This thing is interpreted as this, and this product is actually this. So again, the same thing holds good. Now let's have a look into the third one. Okay. This is interpreted as x to the power lambda mu. Again, this by laws of indices. This is nothing else but x to the power mu to the power lambda. Now this part is this, and this part, the outer part, is this. Okay? So, again it holds good. And finally, this gets interpreted as x to the power 1, which I know is x. So, this also holds good. So the positive real numbers with the scalar multiplication of taking powers, therefore, is a vector space. With vector addition equal to multiplication of reals and scalar multiplication equals to taking powers. Is a vector space. So, this example is esoteric in the sense that we would have had no idea of this example unless we had formalized it in this way, and hence we see the fruits of this formalization already.